Okay, in our instruction book on page 32, we're comparing numbers in scientific notation. Earth is about 1.5 times 10 to the 8 kilometers from the sun, while the planet Neptune is almost 4.5 times 10 to the 9 kilometers from the sun. The distance from Neptune to the sun is about how many times the distance from Earth to the sun. Now, in the video, I gave you two options for working with numbers. You can compare them in scientific notation, or you can compare them in standard form. In the first part, in the model it, they're showing you these numbers in standard form. They've taken these scientific numbers, they've put them in standard form. Now, I also told you in the video that if you want to know how many times greater something is, you put the bigger number on top and the smaller number on bottom, and then you divide. Now, in standard form, you would have, it comes out to 4,500,000,000. The drawback to standard form is all of these zeros. You run such a high risk of getting too many or not enough that it's really better to learn how to do this in scientific notation. Now, let's see, the 1.5 times 10 to the 8 is 150 million. And if you was going to divide these in standard form, you would start by canceling out some of these zeros. Drop a zero here, 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 and here, here, leaving you with 450 divided by 15. And when you divide that out, you would get 30, telling you that it's 30 times the distance from Earth to the sun to Neptune to the sun. Now, the other way to do this was by dividing these using scientific notation. They're going to talk you through this to compare these two numbers. First, compare the constants. These are your constants. Remember, the constants are the number at the beginning that does not have a variable. Okay, so first we would compare those. And we would divide 4.5 by 1.5. And then you would compare the base 10s. And we would divide those. 4.5 was on top, so its base 10 would go on top. And we would divide that by 1.5's base 10, which was 10 to the 8th. Then you just divide these like two separate division problems. 4.5 divided by 1.5 is 3, and 10 to the 9th divided by 10 to the 8th, that's a quotient rule, so you would subtract, giving you 10 to the 1. Now, if you told somebody that it was 3 times 10 to the 1 times greater, that's not going to mean very much to them. So if we want to communicate this number to somebody, we would put it back in standard form. This exponent of 1 says we need to make the 3 one place value larger. Okay, the exponent is positive, so we want to make the number larger. So that number would go from 3 to 30. And it would be 30 times greater. Just like we got in standard form, it's just a different way to do it. All right, the next page is going to kind of walk you through the work that we just did. Number 12 says, look at the first model it on the previous page. You've got 4,500,000,000 is how many times the value of 150 million? We already solved that and we came up with 30. Okay, 30 times. Number 13, look at the second one where we had 4.5 is how many times the value of 1.5? It was 3. Because 4.5 divided by 1.5 equals 3. Number 14, 10 to the 9th is how many times the value of 10 to the 8th? We've already said it was 10 times as great because you had 10 to the 9 divided by 10 to the 8, which is 10 to the 1. And 10 to the 1 equals 10. Look at your answers to problem 13 and 14. 4.5 times 10 to the 9th is how many times the value of 1.5 times 10 to the 8th? Give your answer in scientific notation and standard form. So 3 times 10 to the 1 was our answer in scientific notation. And that was equal to 30 times in standard form. Number 16 is an opinion question. Which method would you use? It's totally up to you. It's your preference. I prefer scientific notation if there's a lot of zeros. If there's not a lot of zeros and it's a number I can work with easily, I prefer standard form. Okay, it's just a personal preference. Use what you just learned to solve these problems and show your work on a separate sheet of paper. 6 times 10 to the negative 5 is how many times the value of 3 times 10 to the negative 8. We've got 2 examples at the bottom of the page. How many times the value, we're going to set this up as division. Now we have to put the bigger number on top and the smaller number on bottom. If you will look at the way they've worded this problem, it says 6 times 10 to the negative 5 is how many times the value of the other number. They're telling you that number is bigger. If you're not sure, you may have to do some comparing. So I'm going to put the bigger number on top, the smaller number on bottom, and then all I have to do is divide. I'm going to divide 6 by 3. I'm going to start with the constants. 6 divided by 3 is 2. Then I'm going to divide my base 10s using the quotient rule, which means I will keep the base and I will subtract the exponents. Negative 5 minus negative 8. This is one of those tricky ones that always gets you. 2 negatives make a positive. Negative 5 plus 8 makes positive 3. Now 2 times 10 to the third doesn't really mean anything to you, but in standard form I'm going to take 2 and I'm going to make it 3 place values bigger. So I'm going to move my decimal 3 places from 2 to 20 to 200 to 2,000. 3 place values bigger than 2. Star A is about 3.4 times 10 to the 18th miles from Earth. Star B is 6.8 times 10 to the 16 miles from Earth. Star A is how many times as far from Earth as Star B. Now, the way that is worded, it tells me that Star A is farther than Star B. So I'm going to put Star A on top. Star A was 3.4 times 10 to the 18th. Now, I'm choosing between standard form and scientific notation. In standard form, I've got to put 17 zeros on that number. I am not interested in counting out 17 zeros. That is why we use scientific notation. 3.4 times 10 to the 18th. Star B was 6.8 times 10 to the 16, which is 2 place values smaller. So if you was comparing these, that one is 2 place values smaller, which would mean it's the smaller number. Now when I divide, I'm going to divide constant by constant. Now 3.4 divided by 6.8, the first thing you should notice is that the bigger number is on bottom and you're kind of going to panic. That's okay. Guys, you can divide. Can we not divide and get a decimal? Sure we can. 3.4 divided by 6.8. Yes, I already know the answer to this. When you type it in, you get 0.5. That is still a number. It is okay to get a decimal. So I've got 0.5. Now I'll keep my multiplication. Now I'm going to compare my base 10s. It is the quotient rule, so I'm going to subtract. 10 to the 18 minus 16 gives me 10 to the 2. Now when I look at this number, the first thing I notice is that the 0.5 is not big enough. Okay, that is too small. I could not leave this as the answer in scientific notation. I would have to move that decimal. I would move it one place to make it 5. And since that made it one place value smaller, it would subtract, and it would give me 10 to the 1. Okay, we used one of those place values by making that 0.5 become a 5. Now, 5 times 10 to the 1 still means nothing. In standard form, I've got to make it one place value bigger, which makes it 50 times greater. At the top of page 34, there is an example. You can read through that. It's talking to you about negative exponents. Number 19, we've got this really big number that none of us can read. They want us to put this number in scientific notation. Now, what I need you to understand is if a number does not have a decimal point, it has an implied decimal at the end. We have to make the constant be between 1 and 9. So I need to move my decimal between the 5 and the 9 so that it becomes 5.974. Now, I do have to show the 9, the 7, and the 4 because they are important. They're significant. Whereas all of those zeros at the end can be dropped off because we're going to represent those with a base 10. Now, every place value that we move the decimal has to be represented on the base 10. We are just going to count. Because this number is greater than 1, okay, we can all agree that's greater than 1, we are going to have a positive exponent. Positive exponent. Then we just count. I've got 1, 2, 3, 4, 5, 6, 9, 12, 15, 18, 21. Don't stop at the 4, okay? We don't want 5,974. We want 5. So we're going to go 3 more to make it 24. And that is your number in scientific notation.
Do you wish you had that much money?
I do. Wish I had that much money. That'd be awesome.
It's good when I can probably read that.
Number 20. Use the information in the table to solve the problem. We've got Mercury, Mars, Neptune, and Pluto, and we are going to write this in scientific notation. Remember, they all have an implied decimal at the end. I need to move that decimal so that the number is between 1 and 9. So I want my decimal to be here between the 3 and the 6 so that I have 3.63. My number was greater than 1, so my exponent will be positive, and then I count. 1, 2, 3, 4, 5, 6, 7. So that one is 3.63 times 10 to the 7th. For Mars, I've got 142 million. I'll use my implied decimal at the end. I want to move it to where it becomes 1.42. And then I count 1, 2, 3, 4, 5, 6, 7, 8. This one had 8 place values represented. Again, the number was greater than 1. We moved it to the left. The exponent is positive. For Neptune, 2,800,000,000. Implied decimal at the end. I need to move it to make the number 2.8. Then I count for my exponent. 1, 2, 3, 4, 5, 6, 7, 8, 9. So that one gets a positive 9. Pluto is 3,670,000,000. The implied decimal is at the end. I need to move it between the 3 and the 6 to make 3.67. Then I count 3, 6, 9 place values, and I give it that exponent of 9. The second part says how Neptune is how many times as far as Mars. So you're going to have Neptune divided by Mars. Neptune was 2.8 times 10 to the 9th, and Mars was 1.42 times 10 to the 8th. And then we would divide. Divide your constants, and then divide your scientific notation. When we divide constant by constant, we get 19.72, And then when we divide our scientific notation, we get 10 to the 1.